Okay, so 5.2, we're going to look at integrals that we can take that will give us a natural log in our answer. Since we now know how to take the derivative of a natural log, we want to see when that process is going to be reversed and which kind of situations are going to give us natural log answers when we're integrating. So the very basic one, since we know that the derivative of a natural log is 1 over x, that means if I integrate 1 over x, I'm going to get the natural log of x, but I have to have absolute value brackets in there because, of course, we can't take the natural log of anything that's less than 0. So, if we integrate something like this and we get the natural log of a number here, in order for our check step to actually work, we have to have this absolute value in there. Same thing for u. So if I've got 1 over u and I've got the du, that'll be ln of u. Another way to write this one would be this way. If I've got u prime over u with a dx, that still turns into the natural log of u. So these are kind of the same thing. It's just a different way of looking at it. So now we'll just start looking at some examples here. Start kind of simple here with this one. I could change this into, if I make this u, okay, so u equals 3 minus x cubed. That means du would have to be negative 3x squared. Okay, so I've got u on the bottom. I've got the x squared part, but I don't have the negative 3, so that means I'm going to have a negative 1/3 in front. Okay, because that's how much of du I have. I have negative 1/3 of du represented here. And then I'm going to have my du. So I've got du over u, which would be the same as 1 over u du, which integrates to be the natural log. So negative 1/3, the natural log of my u, okay, absolute value of 3 minus x cubed. And then we could put this, up here as an exponent if we wanted to, just as a good review for our logarithm rules. Could turn this into the ln of the absolute value of 3 minus x cubed to the negative 1/3 power. Of course, that negative 1/3, the negative puts it in the bottom. So this could be the ln of 1 over the absolute value of 3 minus x cubed to the 1/3 power, which could be rewritten as the cube root. So that's just some things that we can do. Leaving your answer this way or this way is fine. In fact, I'd probably prefer this as to this, because these powers are usually easier to work with than having roots in there. Next example. Okay, here what we've got, I've got a natural log in here. Okay, so I'm probably going to need to make that my u. Okay, and before I do that, what I'm probably going to want to do is bring this 3 down here, because if this is my u, my du would be 1 over x cubed times 3x squared. So I guess I could leave it that way. You do have the option of bringing the 3 down, but what this simplifies to would be 3. Okay, I'd have x squared over x cubed, and those would cancel, leave just an x on the bottom. So that's my du. Now, looking here, I've got 1 over x. Okay, I don't have 3 over x, but I do have the 1 over x. Even though it doesn't look like it, we could rewrite this as the integral of 1 over x over the natural log of x cubed. And then it's a little easier to see that we have our du up here, actually. But we do need the 3, so I would multiply by 3 on the inside, which means I have to offset that by multiplying by 1/3 on the outside. And now this is my du, so I can rewrite this as 1/3 the integral of 1 over u du. And if I integrate that, I know that I'm going to get 1/3 the natural log of u. U happens to be a natural log, so it's the absolute value of the ln of x cubed. Okay, so we kind of have an embedded, a log within a log is what we have. Don't forget your plus c, which I think I forgot on the last one, but you need this plus c on all these since these are indefinite integrals. Okay, so that's a couple examples of things you can do. There's another process that you might run into. Okay, so if you have something like this, you might be thinking that, maybe you want to make the top u. Well, if the top is u, okay, then our du would be the derivative of the top, which would be 3x squared minus 3x plus 4, and we're not going to have that anywhere in here, so that's not going to work. What we're going to want to do to make this into a situation where we can integrate it is to do our long division. Okay, so everybody's favorite, polynomial long division. We're just going to actually figure out what the quotient of these functions are, since I can rewrite this as the top divided by the bottom. And I'm going to do the division to rewrite it in a way that I can integrate. So x squared, to make it match the x cubed, I'm going to multiply it by x. So multiplying this by x, I'm going to get x cubed plus 3x. Okay, and I'm going to want to put that 3x underneath the other x's. Okay, and then I'm going to be subtracting that. So I'm subtracting this and this. This cancels. This drops down. And this turns into x, and then I've got the negative 9 that comes down also. Now to make this match this, I'm going to multiply it by negative 3. It gives me negative 3x squared minus 9. I'm subtracting these. So really this is adding. Okay, so I'm going to plus plus on both of these. This cancels. I get the x down here, and this turns into 0. So this is my remainder. So I'm going to write that as plus x over the divisor. So this is what this actually is. If I actually do the division, this is my answer. So that means that these are equivalent. Okay, the integral of this is the same as the integral of this. And this I can integrate because I've got 1, 2, 3 different terms, and I can integrate all 3 of those. Okay, so the integral of the first term here is just going to be a power rule. So I'm going to raise the power by 1 and drop the reciprocal. So I get 1/2 x squared. The integral of this is just 3x. The integral of this, we can now use our natural log integral rule. So if the bottom is u, then du equals 2x, and I need to multiply by 2 and 1/2 on the outside. So I'm going to have plus 1/2 integral of du over u which turns into 1 over 2, so 1/2 the ln of u, which was x squared plus 3 plus c. Okay, and this would be the integral of this. Okay, now, knowing that the integral of 1 over x, or 1 over u, is ln of the absolute value of u, this allows us to come up with rules for integrating our other trigonometric functions. There's proofs of a couple of these in your book. I'm just going to lay the rules out for you. I've combined it with the ones that we already knew. So we knew the integral of sine of u was the negative cosine of u, since the derivative of negative cosine is sine. We knew this one also. Now we can find you could actually do this one by turning tangent into sine over cosine and having cosine be your u, and then you'd have negative du, and you'd end up with the integral of tangent being the negative natural log of the absolute value of cosine. Okay, cotangent would be very similar. There's kind of a trick that they do to get secant and cosecant, and they go through that in your book. But here's the rule for integrating secant and cosecant. And then these are some other ones that you should know from your derivative rules. Derivative tangent is this, so the integral of this is tangent, and same for these. These rules can be found in the chapter, so section 5.2, page 337. They're also in the very front flap of your book, so just behind the front cover, there's a big table that lists all your differentiation rules, which includes some that we haven't gotten to yet. And your basic integration formulas are on there, and those include these that I've just listed, as well as a couple of that we haven't gotten to yet either. So you should be able to use these combined with all the other tricks that we've learned to integrate all the problems in your assignment.